What is this high UV?
High ultra.
Yeah,
Outside,
It's outside.
of course, rain and solar radiation.
What is this? High UV what?
Ultraviolet radiation.
Oh, where did that go? Oh, it was,
Now
just
it
changed.
shows
Oh,
10%.
it shows automatically. I thought maybe you are using software or something. That's right.
No, it'll show.
I used to weather forecast.
What was it about?
It's about the weather.
Oh, the weather. I see. Oh, yeah, yeah. And so outside, if you go there, it's extra UV. Okay, I didn't pay attention. So these days they have that. Never wear sunscreen, right? I almost thought it was, when you asked, I was going to say high definition because I thought it was a TV property. So I thought it must be high definition. And I was going to give you a theory on that. So there was a homework due today. How's it going, by the way? Because I did not complete the calculation in class that I asked you guys to refer.
I still have a good amount to do, so.
But it is program you guys can manage, right? So I can keep proceeding, or do you want me to go back? Can I proceed
Yeah.
forward and you guys take your time?
We
To
can
do
go
the-
on. Only else you said last.
Yeah, that's okay, right?
Yeah.
So just take your time to do it. You don't have to submit it today, but surely not more than Tuesday. Let's finish this up. Because it will very quickly pile up and now exams are coming, exam week is coming, so you don't want to delay. Like if I post, it's okay for me to postpone it, it's just that think of it as a small push. Feel if you're really pressed, then have an extension, but otherwise get it done. And that's how this works.
So our exam at May 5th.
Oh, yeah, I was gonna write that. So let's
Exams.
Quantities.
Yeah, and we have quantum mechanics complex syllabus. How syllabus?
what?
After the quantum mechanics, you have the comprehensive exam.
Yeah, it's comprehensive here also, by the way.
Really?
Wasn't it this way last year?
Yeah. Last year it was comprehensive.
Yeah, May 5th, Thursday, 10:15 to 12:15. I have an exam right before that also, so 2 exams in a row. But I don't take I only give the exam. Okay. Okay, so we have talked about radiation from a localized region of space where all the sources are, and if you're moving, if the charges there are moving, which is mostly done by changing the current. Think of an antenna again. If you change the current in an antenna, you get a signal somewhere very far away. We have done this in the far field approximation. If the regions are far, we could get exact solutions to them. And that's how antennas are actually designed. And these days, of course, you can do much better than what I introduced, very small, it's a glimpse of what actually they managed to achieve. But everything was done in the time domain. Now you would like to talk about frequency. Often antennas deal with frequency dependence. You talk about what's the frequency of the signal that is coming in. So you would like to know the frequency dependence of the radiation also. So that plays an important role in engineering that. So the idea is, let's do the whole thing that we did, starting from the scratch, electric potential, Maxwell square, everything, go back and do it in the frequency domain, and pretty much repetition of what we did in the last 2 weeks in the frequency domain. Okay. And you'll pretty much get a prescription of how to go from time to frequency, which we have already many times I have pointed out. Basically, whenever you get a time derivative, what do you replace to get a frequency? How do you go from the time domain to frequency domain?
Fourier transform.
Yeah, Fourier transform, but that is an easy way of doing it.
I omega.
Yeah.
Correct. Derivative is replaced with just I omega or minus I omega, and you get the so it's in many ways easier because you don't have to take a derivative. It becomes algebraic. All the time derivatives become algebraic. So sometimes it's even easier to do that. So let's talk about that. So we are saying radiation and frequency domain. So let's go all the way back to Maxwell's equation itself. The main idea is Fourier transform. So Fourier transform is got by time derivative is replaced with, depends on the definition of your Fourier transform. In the what we are doing, it is minus I. And all the time dependence is switched to frequency dependence. And that's pretty much what it is. So let's write down our Maxwell's equation itself. So Maxwell's equations are divergence of electric field, which is R times T, right? But now I'm going to write omega. This is the Fourier transform of the time dependent electric field. That's equal to charge density, which also becomes Fourier transform. Right? So that's all. You have to explicitly do this. Like you should at least take one equation. So let's this be a quiz. At least start from this equation, start from your time domain, and do the explicit Fourier transformation and get this. Okay. Is that clear what to do? So start from the time domain, Fourier transform it, and get this equation. Not do without using this prescription. Okay. So to turn out that always you do that, you get it. But at least once you should do it for this particular lecture. You've done this before, various places in the first semester. So, okay, is that clear how to proceed? Yes, that serves as a quiz. Divergence of the magnetic field, similarly. Or omega, instead of time dependence, it's omega, that's equal to 0. And they'll cross the curl of the electric field. Now, instead of time dependence, it's omega dependent. And that's where you start getting, this is negative time derivative of magnetic field. But now if you say negative time derivative is plus I omega times B times omega. And I'll cross H, which we can write as mu, right? So this is H. Let me write H. This is minus I omega electric field or omega. Something missing, right? That should be D. And no, what are they? This is correct, yeah. Correct. I can write this. I can this also. I can write as D. Yes, please. Go ahead. Did I mess up?
Plus G.
Yeah, plus right. This one.
Yeah.
Yes, it's plus plus J R omega. Yep. And we don't have any materials here. So this is, we do not have any materials. In the absence of materials, D is just epsilon naught E, and B is mu naught times H. If there is a material, one should be more careful. Then we have to introduce causality. Then this has a frequency dependence, and in the frequency domain, they are just multiplicative, and it comes out nicely. But here we are just doing it in vacuum. Right? There is no material, so let's not get distracted. Okay. Next, we introduce potentials. So going all the way there, then you do potentials. You would say electric field is negative gradient of phi minus dA by dt times A, right? That's your, this is in time domain. In frequency domain, this will become d by dt becomes minus I omega, right? So I just have to replace this with plus I omega times A. All omega dependence assumed there. And your magnetic field is curl of the vector potential. And it's good to write your differential equation itself, the wave equation satisfied. So there was this gauge we use, right? So what is the gauge we use? Coulomb, or now we are in the time dependent domain. We don't use to Coulomb, we go to the Lorentz, right? And the Lorentz gauge is del dotted with A. And it is so it is plus d by dt over c squared of phi. That's equal to 0. But now we have to change this to frequency. So d by dt becomes I omega. So this is I omega over c squared times phi. This is equal to 0. Right? That's your Coulomb gauge. And your wave equation is minus del square. And it is plus 1 over c squared times time derivative dt squared of phi of r comma t is equal to 1 over epsilon naught times del cube r minus r prime and delta of t minus t prime. Right, that's your wave. That's your differential equation for the electric potential. But now I am interested in writing this in the Fourier space in the frequency domain. Straightforward, that all the time derivatives will become I omega minus I omega. There is a square of this. Minus goes away in the square. I square is minus 1. So this is minus of is that right? That's correct. Yeah, minus of omega square over c square. Okay. And I should change this to frequency. Now notice this is t minus t prime, right? There's a delta function in t minus t prime. Delta function, what's the Fourier transform of delta function, by the way? Do it. How do you do the Fourier transform?
IW.
Huh?
It's just IW.
I omega, you mean?
I mean, I'm sorry. Yeah, I am.
No. Do it. Do the integral. Try it, I mean.
It will be exponential of minus I omega.
Correct, very good, very good. So basically, intuitively speaking, if you have a single frequency, there's only one frequency that contributes. Like think of a sine function which has a frequency. If you Fourier transform means give me the frequency. Out of the whole frequency set, there is only one frequency that contributes. And that's the delta function. Omega is equal to that frequency contributes, otherwise it doesn't. Mathematically speaking, so let's say there is delta of x, right? So this is your f, right? So your f of k would be the x e raised to I, let's say minus ikx and f of x, right? That's your Fourier transform. So do the integral, it's minus infinity to plus infinity. This is, let me say this is x minus x naught, right? Instead of saying x equal to 0, it's x minus x naught. So that's e raised to minus ikx times delta of x minus x naught. Delta function integral is trivial. Replace x with x naught and the integral is gone. So it's minus ikx naught. This is having a sine and a cosine. So what it means is that if you have this to be your in this space, in the Fourier space, so that means this is e raised to ikx, that's a sine function. What are we talking about? If you give me a music, Fourier transform tells you what is the frequency, how many frequencies do you need to build this. And in this case, there is only one wave, right? Only one frequency. So you have to say that k is or x is equal to x naught. That's what you say. So there is only one frequency, or in this case, it's only one position. Either way, you can. So is that clear? The motivation or the insight associated with that?
So if I give you a music, I mean basically I am giving you a wave. And if somebody Fourier transform it.
The way to see it is that out of all possible tones, out of all possible waves, so there is one, so this is one wave, right? I can have a smaller wave, right? There is even smaller wave. Think of all possible frequencies, right? And then you say that standard music, let us say, who's the most popular musician these days, right? Or Vivaldi, let's say classical music, like Vivaldi, if you want to build it. So you put in, okay, 1 of this, 2 amplitude of this, 3 amplitude of this. That is a combination that you can use to build a music. And there's always such a combination. That's a theorem that give me any music you want to. Given appropriate amplitudes, you can build any music. This is a special music in the sense that there is only one tone. You just use a guitar as a pure, you just pluck it once, that is a pure tone. There's only one frequency that is built. In the frequency space, what is that information if you were to talk in terms of frequency now? So this is now in time, right? If you were to talk in terms of frequency, it means that, oops, there's only one frequency. Right? You can say that this is 1 and 0. Instead, you say that because the total sum has to be equal to 1. Right? So this has to be a delta function. Is that clear? That's an idea associated with it. Another way of saying it is that if it is x minus x naught, then, or if it is just delta of x, this is 1. So here you will just get rid of this and just say 1. So delta function Fourier transform is just 1, or the exponential, particular exponential that we're talking about. Since it is t minus t prime, we just need 1. That's a motivation. And yeah, is that clear? Yes.
So why is it not e to the negative I t prime?
Because I am. Why is it not negative r prime? Because I am Fourier transforming t minus t prime. Here also there was a, yeah, so what I'm Fourier transforming in that case is, so let's go back. So there is this, no, this is not delta, this is wrong, right? I should charge density here, right? So I'm jumping ahead. There's a Green's function there. So this is R T. I was jumping ahead. There is a Green's function that's going to come in the next step. So I was thinking about that. So this is R omega. That's all. So next step when it comes, I'll answer the question why it is. So this is just R omega. Sorry. Good question. Okay. Why is that T minus T? Okay, so that's your wave equation in frequency space. And we'll come back to the Green's function in a minute. And this is negative minus omega square over c square A or omega is equal to mu naught times J or omega. Good. To solve a differential equation like this, we build Green's functions, right? So now we build a Green's function in this frequency space, and that will be, so earlier we had the Green's function like this, minus plus actually 1 over c square, e square, dt square times Green's function, g r comma r prime, but this was of the form r minus r prime. After our experience, it's clear that it is r minus r prime and t minus t prime that shows up. And our Green's function we built was r minus r prime, t minus t prime. One can also motivate why it should be r minus r prime based on symmetries associated with it, but at this point, just say that it is. It should be translationally symmetric. I think that's the way to put it. If we translate the source and everything in the universe, everything remains the same. Clear? Okay. Let's do this frequency. We have to move this to frequency domain. So you would use the same prescription, square minus omega square over c square. This is g of r minus r prime, and now this is equal to, I would put this, the d cube r minus r prime, and I would do something with this. So now the question was, you asked the question, if function is delta of x minus x naught, you get this, but what if I had started here itself? So notice that I can translate this. I can also say that f of k is equal to the x e raised to minus high k. I'm not Fourier transforming x, I'm Fourier transforming x minus x naught. In that case, I will have this as my Fourier transform. So I'm using t minus t prime as my variable. T minus t prime is the variable. In that case, I'll get a delta of x minus x naught, and that is equal to 1. Same idea as why x was 1. If x naught was 0, that will be equal to. Is that clear? And that's why that's 1. Here, this is getting t minus t prime is getting transformed to omega. So delta of t minus t prime goes to 1. If I had transformed only t, then I'll be left out with t prime, and then I'll need an exponential. Is that clear? So that answers that question. You're not satisfied. Not satisfied. Okay, that's all. I thought you would ask a question. Okay, you're not satisfied. Okay, let's see.
I mean, this t minus t prime and r minus f still a bit confused with this.
Okay, so let's do this explicitly. Why do this as a step? Whenever in a doubt, just do it explicitly, right? Why use the prescription at all? So let's say, let me take only one term. Okay, so I have second derivative of t squared. Yeah, let's just do the whole thing. C squared plus L squared. And let me just say g is a function of t minus t prime. I'm just suppressing everything else. And that's equal to, let's say, delta cube of r minus r prime and delta of t minus t prime. Fourier transform this, so g of t minus t prime as the Fourier transform would be d omega over 2 pi minus infinity to plus infinity e raised to minus I omega. And I'm interested in Fourier transforming t minus t prime, so I write this as t minus t prime. And whatever is the Fourier transform, we will call that omega. So I will often we just drop that. It's a new function. It should be detailed in another function, but that's my definition of Fourier transform. In that same definition, I have also Fourier transform delta of t minus t prime, and that will be minus infinity plus infinity d omega over 2 pi exponential of minus I omega t minus t prime. Right. This is 1. Right. So that's the definition of delta function if you want. Delta function, this is equal to delta function. So in this way also you can see that the Fourier transform of this is 1. Fourier transform of this is g of omega. Fourier transform of delta function is 1. Clear? Put this back in the equation and we get minus square plus 1 over c square times g of omega is equal to, on the right side, there is a delta function. Okay, clear? So this is how you would do any of this equation. That's how you would like to proceed. Time derivative hits t, and now it is only in the exponential. After you Fourier transform, this doesn't have any t. Right? The only place where time hits is in the exponential and in this exponential. That's all. Move this. So this is a frequent integration and frequency. I can move this derivatives in, operate the derivatives, and what I get is, so now let me write this as minus infinity to plus infinity. It's still visible. D d omega over 2 pi and operate this on the exponentials. And this can be written as e raised to minus I omega t minus t prime. Enter it through. It's minus del square minus omega square over c square. Small brackets. And g of omega. And there is the same thing in here. I can move this aside and write it as minus delta cube or minus r prime is equal to 0. Is that clear? Right, I just moved it here on the side. Any questions? Okay. This is an integral, but these are like vectors, right? These are complete functions. Fourier functions are complete functions. So this is like a vector space. So if sum of these quantities is 0, so each amplitude is 0. Like this is like the amplitude for these functions. It's like a vector. This should be read as A1 I hat or E1 plus A2 E2 is equal to 0. If E1 and E2 are vectors, then A1 and E2 is 0, right? Similarly, each of this is a unit vector. It's called the eigenfunctions. So these are Fourier eigenfunctions. So each of its amplitude is 0. If this is equal to 0, that means every amplitude is 0. This implies that minus del square minus omega square over c square and g omega is equal to delta q. So clear? And that's what I did by hand wavingly. That becomes omega, this becomes 1. Because that's 1. Right? So that was a key. Clear how it went through? But that's the details, but you can jump. Okay. We can solve this Green's function explicitly, but we can also start from this solution and Fourier transform to get this. So that's what we have been doing instead of actually redoing the whole formula. We're just trying to transform. What was the solution here? You guys remember what was the solution? Solution was, this is for a point charge, right? Yeah, 1 by 4 pi, good. R minus R prime, yeah, very good. And what's the time dependence? That's for a point charge, static. But what's the time dependence in this? No, no rho, right? It's a retardation. It's delta function, right? So it is t, delta of t minus tr, right? So t minus tr if you want, but I'll write it as explicitly. So t minus t prime minus r prime over c. The time is retarded. That's your solution, correct? So the solution for this should be the Fourier transform of this. That's it, right? That's all we have to do, right? So instead of solving this differential equation, we use this Fourier transform. What would be the Fourier transform of this? Naively speaking, from what we did just now, Fourier transform of delta function. What is it?
1
or
e to the power minus.
exponential, right? So we should have that exponential coming up, where the exponential will be the retardation should show up. So this will go up in the exponential. T minus t prime gets replaced with this. So let's Fourier transform this. So G of R minus R prime omega is equal to the Fourier transform. This time we have to do the dt. It's not the d omega, we are doing the opposite way. So this is exponential of I omega t minus t prime of G. Is that clear? The Fourier transform of G will be given by this. Substitute this in here, we should be able to get the Fourier transform. So let's substitute that. It's equal to T minus G prime, when G is 1 over 4 pi 1 over R minus R prime, and the delta function is T minus T prime minus R prime over C. This doesn't have any time dependence, so I can move it to the left. So this is your point charge. Notice if you're in a static case, you just have this. So whatever I write next is the time dependent part contributing to it. It's minus infinity plus infinity dt exponential of I omega t minus t prime times the delta function of t minus t prime minus R minus prime over C. Delta functions are evaluated by replacing t with whatever is argument by equating the argument of the delta function to 0. When I set the argument of delta function to 0, t minus t prime is nothing but R minus R prime over C. So I just have to replace that. So this is equal to exponential of I omega and R minus R prime over C divided by 4 pi. Okay. That's your electric potential in the frequency space. Okay, so that's your G in frequency space. If you're in frequency space, how do you get the static case? So there is a function that is a frequency dependent function. Okay. And I say that this corresponds to a system where there is no time dependence. How is time dependence? Time independence. Right? Time independence means static case. How is static case shown in the frequency space?
One wave.
Yeah, think about it. Yeah, one wave, that's good. In particular, which wave? Which particular wave? One wave, you're correct. No, something is static. What is a time period? If something has some
A standing wave?
no, I'm saying suppose there is a static case. Static means there is no time dependence. That means time period of that would be how long? Like when does the system repeat itself? Think of a static. So there is something happening which has no time dependence in it. but you want to see it as a repetition. How long does it take to repeat? It never repeats, correct? It never repeats. Time period is infinity. That's the way to look at it. Okay. So time independence is equivalent to saying time period is infinity. If time period is infinity, what is frequency? Which wave? You said one particular frequency contributes. Which particular frequency contributes? If time period is infinity, what is frequency? Frequency is 0. So you want to set frequency to 0. If you are in the frequency domain, omega equal to 0 means the time independent static case. So let's set omega equal to 0. That should give me my static case, right? And indeed, omega equal to 0, exponential of 0 is 1. That's my static case, right? Which is good, right? That matches with. Is that clear what I mean? How I interpret that static case to be the frequency 0 contribution. Those are simple interpretations. Okay. Okay, so now we have our Green's function. If we have our Green's function, then we should be able to, so now I can do this here, right? I can use this equation and write my Green's function or solution for the phi in the frequency domain in terms of the current in the frequency domain. Yeah. So phi of r omega is equal to invert this solution, right? This Green's function, which is 1 over epsilon naught dq r prime times exponential. No, Green's function, right? Green's function first. Let's do this in 2 steps. So Green's function r minus r prime and rho of r prime domain, right? That's how you get that's how you invert this differential equation. So whenever you have a differential equation, if you know the corresponding Green's function, it's given by the Green's function. It's a superposition principle if you want. If you know the point charge, then it's a sum of all the point charges. So this is the amplitude for the point charge. This is the electric potential in the point charge. Right. So that's equal to 1 over 4 pi epsilon naught dq r prime exponential of I omega over c r minus r prime, and here it is rho r prime omega over r minus r prime. That's it. So now, okay, clear. Any questions? Yes.
Yeah, I just have, so when we look at the static case, do we like, so does our R prime like also change in the static case?
No, right? R prime, see the way I have written it, there is no T prime dependence in R prime. This is just some coordinate here. So the only time dependence shows up in this omega. That's the only thing. This is in principle, if I bring in dynamics, the moment I say that R prime is a charge which is oscillating, then there is a time dependence in here. But at this point, I'm not saying that. Right. At this point, R prime is just a coordinate in there. If I bring in the dynamics, then yes, that will be having a time dependence. If I say that R prime is a coordinate of a charge, then there is a time dependence. Good point. Yes. But at this point, we are just saying that there is an R prime there, and whatever happens at that, just R prime is there. That's all. Okay. So that's, and this is pretty much exact, right? At this point, this is exact. This is not radiation. Radiation has this feature that we are localized in one region and we are observing very far away region, right? This has not used that approximation yet. This is exact. If you want to do any charge problem, we have only Fourier transformed it. It's only saying that we are doing it in the frequency domain. And already the simplicity is clear here. So if you can do this and you go back to your time domain, you get exact solution, even if you're very close to that charge. But we are interested in the faraway regime, and let's say that's a radiation approximation, or let's say far field approximation. Let's call this far field approximation. Far field approximation is basically saying that R minus R prime then is the magnitude of that is simply R and minus of R hat dotted with R prime. That's what we did. R hat dotted with. And that should be higher order terms, but we are neglecting. That's how we go from a standard solution to far field approximation. Clear? Put that approximation in here. Since it is in the denominator, I need to keep only the leading order there. And if this one, I need to keep both terms. So this is equal to phi or omega. So now it's the far field approximation. Epsilon naught. This is E cube prime, and this is I omega over C, and I keep both terms down. So this is R minus R hat dotted in R prime. Notice in the denominator, I don't keep the second term, saying that that's a higher order term. Okay. That's equal to, we are integrating on R prime. Earlier, I couldn't have taken R out because this comes as a combination, right? R minus R prime. But now I can bring this out. This is not having any R prime dependence. This can come out, and even this can come out. So this is, I think, 1 over 4 pi epsilon naught. Remember what is happening here? We have some sources which is R prime here, and there is an R which is very far away. If you're saying in the first approximation, there is just this R that is contributing. This is the R, right? That's the first approximation, right? That's a potential. I omega over C R over R, right? That's a Green's function. If I were to approximate this to be my source, if I neglect the position of it. And this D cube or prime The rest is e raised to minus I omega over c r hat. Started with prime. That's clear. Like just that approximation gives us a significant boost in the sense that suddenly things are tractable. Otherwise, you cannot proceed much beyond this unless you give me the charge density. Currently, we are still in a general charge density. Okay, with me? Okay. This looks very much like a Fourier transform, like exponential function, right? But now this is not a Fourier transform in frequency. This is a Fourier transform in R prime, right? Even though we were working in the frequency space, just by doing this transformation, it seems like whatever is your electric potential in the position is apparently given in terms of a Fourier transform, except that this is not a K there, right? Fourier transform in position will have a wavelength in there, but it's not a wavelength, but something else of this kind. So let's define, right? Let's define. So define. So let me define K as K is going to be equal to omega over C. That's like if you have a wave, electromagnetic wave, that's the magnitude of that wave, right? But I need to give a direction also to this. Direction is going to be R hat. Okay. So what's the interpretation of this? This is a direction of propagation. K is associated with the direction of propagation. We are talking about a direction in the R hat direction. And that's R hat observation. From the origin to the R hat, not from the source, from the origin to the observation point, and having frequency deciding your wavelength. Is that clear? So I have defined a wavelength now, even though we were talking about frequency, right? Time domain, but automatically I have a frequency wavelength there. So this is 2 pi over wavelength times R hat, where lambda, so 2 pi over lambda is omega over C, right? So omega fixes your wavelength. In that way of writing, I have R comma omega is equal to 1 over 4 pi epsilon naught. I can write this as a magnitude. Notice this is not a vector. E raised to I k r is the magnitude of the propagation term, R, and this is d cubed or prime exponential of minus I k vector k divided with R prime. Right, again, K is in this direction, right? K is in this direction, and that's K. That's a definition. This is the definition of a Fourier transform. So what I have is 4 pi epsilon naught e raised to I k r over r times the charge density in the Fourier space. This is remarkable because there is nothing to do now. This is the solution for any charge density. In the time domain, we had to do an integral, correct, to get the electric potential. Electric potential is already solved. If you know the charge density and if you know the Fourier transform of the charge density, you immediately know the electric potential, no work needed. What is the R dependence? R dependence is completely here. R and R. This has R dependence, but this R dependence is in the direction only. There is only the R hat that is coming up with K with the omega over C. So this is actually, so this is omega over C times R hat. Right? So the R dependence in this is of this kind. So it's only the direction that is important when you vary. So that's like saying the dome, right? Dome effect. When you're on the dome, all the R dependencies of this kind. That's only the direction. It's only a theta phi dependence, right? It has only a R hat dependence in there. Is that clear? So that's a significant simplicity there. And if we know electric potential, the same idea goes through. Our omega is equal to 1 over 4 pi epsilon naught e raised to I k r over r and rho of k omega. So repetition that. The vector potential goes through the same ideas, right? Vector potential is the same differential equation. I only have to replace rho with j and epsilon naught with 1 over mu naught. So this will be equal to mu naught over 4 pi e raised to I k r over r, and this time the current density.
A1 you wrote, we deduce it your this.
Say that again?
The external for A.
Is this what you mean? Tell again?
So you deduced it, I mean, how will you find the external for A?
Oh, A because, okay, phi, how did I start? I started from this equation, correct? For phi, and inverted this and I reached here. But A satisfies exactly the same thing. If I replace phi with A, rho with J, and epsilon naught with 1 over mu naught, I get that solution. So I don't have to really do anything. I do that same transcription, rho with J, epsilon naught with 1 over mu naught. That's all I have to do. You don't really have to do any work there. If you do it, it will be exactly the same steps. Okay.
Yeah. Thank you.
Any other questions? Given the potentials, we have to go for the electric and magnetic field. Correct? Electric and magnetic field is somewhere here. We were right. Let's test this. But now, so electric and magnetic field, electric field is, this is now in the frequency domain. That's gradient of phi minus I omega, so plus I omega times A. I have to take the gradient, right? Gradient now hits on this R, it's on this R, and it's on this K there. right? So it seems like there is a lot of things it can depend on, but the key is, so let's actually do this for one. So, should I say fine and jump? Now let's do this, okay? So let's do gradient of phi. So gradient of phi is equal to 3 places, correct? So this is gradient of 1 over 4 pi epsilon naught e raised to I k r over r, and then there is rho of omega over c times r hat, right? Or which is the same as k r hat, and this is omega. And it has to hit all. This will hit this piece, and this piece. Correct. We are interested in the leading order. The leading order, when you hit this r, it will become a 1 over r squared. Derivative of 1 over r is a 1 over r squared. Derivative of this r, since it's in the exponential, it will bring out I times k. So it doesn't change the order of r. Right? If I hit here, this is like saying r hat is equal to vector r over r. As all this has an r in it in the denominator. So that will also increase the order. So this is what is the leading term here. So these two are higher orders. This is the leading order. Why? Because there is a denominator r, there is a denominator r. Right? So this is what gives you the leading term. And I still need the direction of it. Gradient of r, remember, is r hat. So when this hits your IKR, so the main idea is that gradient of k times r is nothing but k times r hat, which is k. So this is the same as I times k vector times 1 over 4 pi epsilon naught e raised to I k r over r times rho of k prime k omega plus higher terms. So another way of looking at it is, in the radiation approximation, far field approximation, right? I have been calling it far field approximation. It is very close to what's the radiation approximation. Gradient is simply I times vector k. See this gradient, it's just 5 times k. So whenever you're doing far field problems, Fourier transform is really straightforward. All the time derivatives, replace it with minus I omega. All the gradient, replace it with I times k vector. And you get the equations that decide your far field approximation. Is that clear? There is an argument in here. There is 1, 2, 3 terms. This is 1 over r, that gives you 1 over r squared. This has a vector r over r that also is higher order. So this is the primary p square that comes from. Okay. So it's a detail in there. With this, we know electric field now. Electric field then in the frequency domain, r omega is equal to minus ik hat or I minus ik vector k times phi of r phi of k omega, right? Or phi of r omega, sorry. Phi of r omega and plus I omega times vector A of r omega. That's your electric field. Magnetic field similarly is equal to del cross, right? Wherever there is a gradient, you have to replace your ik. So this is ik, vector ik crossed with A of r omega. Where A of r omega is this. Clear? A little quick. Hurry a little. One more step and we're almost there. And then we'll begin next. We would like to process this a little bit, right? And for that, let's go back and see how it looks like. Let's replace phi from these things into that. Right? So your B is equal to, B is ik times A. So that's your k times j, right? So it is, how do I want to write this? Ik times j. So that's I omega over c times r hat crossed with j, which is mu naught over 4 pi times e raised to ik r over r times j. Okay. Omega. Rewrite it in a certain form. This is r hat crossed with, right? This is r hat crossed with, I have mu naught over 4 pi e raised to ik r over r. So that's taken care of. And eventually that is I omega over c times j. Okay, omega. It's good to think of B, C times B. Omega, so I multiplied by C, so it's C, right? Remember that is the resistance radiation impedance of the vacuum. That's one way of expressing. Similarly, electric field would be equal to, I have to do the same thing in here, and that will be in terms of rho and A. So electric field is ik hat, so I have to collect everything together. So this is minus ik vector, right? I omega c times r hat, I omega c times r hat times phi, which is 1 over 4 pi epsilon naught, and e raised to ik r over r times rho, and plus I omega times A, which is mu naught over 4 pi e raised to ik r over r times j. That's the same as from this Let's bring this out. Yeah, so this can be written as, let me bring out as much of this as possible, right? So mu naught times C, right? This is all there, omega over C, everything is in there. So let me write this, mu naught C over 4 pi times I omega over C times J. That whole thing is just not C, I exponential, forgot. So this is exponential IKR over R I omega over C times J. That's pretty much whatever is in that the bracket, and that's the same as this. Mu naught C over 4 pi I omega over C e raised to IKR J. That's pretty much what this is. Let's write this also as much as possible like this. So this is equal to mu naught C over 4 pi e raised to IK R over R, and that is I omega over C this time, just that this is rho. And that is an R hat. Otherwise, most of it is there. Okay, so now this is mu naught over C epsilon. Have I got everything? So this is 1 over mu naught C, and that is an epsilon now. So that's the extra term in here. Otherwise, and that is a minus sign. But this is nothing but C squared, so I can put a C on the top, and that is all that I need, right? So that is it, C squared, that's C. So this extra term here is times C. So that's your plus. Couple of more minutes, and if you notice, this is nothing but take everything common out. This is mu naught C over 4 pi exponential IKR over R I omega over C, and this is C times rho times R hat. So this is C times rho or omega times R hat plus J. And we want to see what that is, and this we will come next time and process this. So this will come out to be exactly J itself. This will come out to be R hat crossed with R hat crossed with J. Using conservation of charge. We'll come to that. Okay. You? Yeah.
Is it supposed to be R omega or K omega?
Which one?
For the dependencies of J and rho.
J, yes, it is K. At this point, we are writing everything in terms of Fourier. We'll come back to that. Oops. Oh, because that's wrong. That's how the cross product comes. It's not really clear, but remember that d rho over dt plus del dotted with j is equal to 0. So this allows me in the Fourier space to replace j with rho or rho with j. So in the Fourier space, this will become minus I omega times rho plus del becomes ik dotted with j is equal to 0. So this is nothing but minus I omega rho plus I omega over c times r hat dotted with j is equal to 0. Omega cancels, I cancels, so rho is equal to c times rho is actually r hat dotted with j. And that I can replace in here, and that gives me my cross product. So that we will do next time. So that's a, I would have liked to complete it, but I think that is still okay, good. Yeah.
Thank you.